Welcome to this retronet call about the X.21 interface. This is not a very in-depth technical talk. I don't think we will fill an hour with that. It's only a few slides that show some kind of introduction into what X.21 is and how it works. And it reflects my research into that historical topic so far. I was using X.21 with Cisco routers and other equipment back in the day, but I never really implemented it. In this context here, in this talk, we will also look at particularly at the use of X.21 in circuit switched networks. If you've seen my previous talk on the DATEX-L network, the German circuit switch packet data network of the 1970s and 80s and 90s to some extent, then this basically now focuses on a specific area, which is the interface that is used as a user interface of that network. And so all of the information here is from books, specs, and articles. If you know something better or have corrections, amendments, please let me know. Of course, always some things are simplified to make it more accessible. So what is X.21 at all? It's a bit synchronous serial interface. It's traditionally been used from 1976 onwards through the 1980s by circuit switch packet data networks. These were public networks operated in parallel to the telephony network with their own infrastructure, and the interface to the user was, for example, done via X.21. Later also, you could find some ISDN devices offering X.21 as an interface towards the user. That was probably primarily meant as a migration path from legacy terminal equipment, legacy user equipment that was used with those circuit switch packet data networks, and then it was migrated over to ISDN. So you can find ISDN terminal adapters that have X.21 interfaces. And you can also find equipment, for example, these so-called Musiktaxis, how we call it in German. I think internationally it's more like an audio codec for transmitting better than phone or better than ISDN quality voice, which was used by radio stations for remote transmission of of audio. And a number of these that I've seen, for example, have X.21 also as a user interface. I'm not sure why exactly that is, but yeah. Also, X.21 has found a number of use cases later by carrier leased lines. So if you wanted to have a data connection between two locations somewhere in a city, in a country, then you could rent a service, a bit transparent service, a synchronous service between typically 64K on the lower end and later in the 90s and 2 megabits on the higher end. And the operator then would put some data communications equipment in your site, and the user interface to that is then X.21. And that's the reason why you can find X.21 interfaces for a lot of Cisco and other competitor router devices of that era, so that you can use these data links which were provided as synchronous serial interfaces with X.21. The main specification is ITU technical recommendation X.21, and hence the name. But X.21 really is not much more than a collection of pointers to all kinds of other specs. So that includes the entire X20 series, particularly I think X24, X25, X26, and X27, well, 29 as well. And also that then references, again, other ITU specs all over the place. So yeah, it's a serial interface in the first place. So serial means that bits are transmitted successively one after the other. unlike parallel interfaces, for example. Most people are familiar with PC serial ports, and they're often called RS-232, even though they implement only a small subset of RS-232, but that's what people mostly recognize as a serial interface. And any microcontroller of the last decades has typically serial interfaces built in, provided by so-called UART, Universal Asynchronous Receiver and Transmitter. And these serial interfaces that most people are familiar with are, however, asynchronous, while X.21 is a synchronous interface, so there's a significant difference between those two. A synchronous interface means that the receiver and transmitter share a common clock, and then the bits are transmitted, each one within that synchronous clock. In a simple use case like in X.21, it's indeed 1 bit per clock cycle. The advantage of synchronous interfaces, and that's, I think, why they were used back in the day, is that you don't need start and stop bits, so you have a higher user data throughput. So if you compare, let's say you have a 9600 BPS serial link, and you use asynchronous transmission like a normal PC serial port, then you have an 8-bit byte plus start and or stop bits, and these start or stop bits are not needed in case of a synchronous interface, so you get higher throughput in terms of user bytes per bit compared to the, so you need at least 9 bits in case of a UART for every 8-bit, and here you actually have fully transparent, all 8 bits are transmitted, and then you start the next 8 bits without any additional overhead. The simple synchronous interfaces like X.21 need separate wires for clock, so you don't just have like on a RS-232 style UART, where you have, let's say, an RxD and a TxD line for receive and transmit data. In addition, on a synchronous interface of this sort, you have additional clock lines, clock signals. So there is an overhead on the electrical side. You need more wires and more transmitters, more receivers, and so on in your electronics. Some example for other synchronous serial interfaces that people might have played with or are familiar with, for example, SPI or I2C, which both again have their own clock lines alongside with the data lines. SPI is maybe closer to like on the like electrical. Well, no, it's anyway. Forget about it. I2C uses a single wire for both directions, whereas SPI uses separate wires. So SPI is maybe closer to X.21 if you want to put it that way. Sometimes you find microcontrollers that have peripherals called USART, which then means a UART that's extended to also have synchronous capabilities and not just asynchronous capabilities. Yeah, so we have a synchronous interface in case of X.21. And in what kind of use cases do we see, or did we see X.21? Similar to the RS-232 and the V-series ITU interfaces, it's specified to be an interface between a DCE and a DTE. And the DTE is the data terminal equipment. Think of a serial terminal, TTY, something like that, or a computer. And a DCE is a data communications equipment. Most people will have worked with or know about modems or ISDN terminal adapters, or in this context of X.21, for example, the DAG or DFG, the German type of equipment that was used with the DATEX-L CSPDN. In classic telco networks, the DCE was owned and provided by the telco, and the DTE was owned and provided by the user. So this interface between DTE and DCE was the user interface of the public communication network. Excuse me. And that's the same also for the V-series interface, which are more like RS-232 asynchronous interfaces with modems. If you wanted to have a modem before the 1980s, in Germany, it was normal that the modem itself, being the DCE, is provided by the postal operator. and you have a asynchronous serial interface before X.21, or another synchronous interface before X.21 as a user interface. So not the telephone line was the interface, but the data interface between DTE and DCE. Yeah, the signal naming and directions in all of these serial interfaces are always from the point of the data terminal equipment, meaning that if something is called transmit, then it means the data terminal equipment transmits, which means logically the data communications equipment is receiving it, and vice versa. So what kind of logical signals do we have in X.21? This is a list of the 6 signals that exist. There are multiple electrical or physical incarnations, which we will look at later. Let's look at the signals first. So we have transmit, control, receive, indication, signal element timing, and byte timing. I indicated directions here. We will look in the next couple of slides in a bit more detail at those signals and what they do and how they are used. So the logical signals in the direction DTE to DCE. So that's what your computer or terminal or whatever you attach your teletext device or whatever you attach to your X.21 interface as a user transmits. So there's 2 signals. One is called transmit, the other is called control. Transmit is what is used to transmit actual data, meaning your serial bit stream. This signal is used both during the call setup phase and during the data transfer phase. Because one important aspect of X.21 is not only to communicate a serial bit stream, but also to be able to signal the call setup and call release. So basically the signaling of a circuit switch network. So you need to dial whom you want to dial up to, and this needs to be communicated to the digital exchange to which you're connected with your X.21 interface. And the exchange needs to feed back status information like unknown number or busy or all these things that also exist in a telephone network, but of course here in a fully digital way. And that also happens over the transmit line, but in combination with the control line. So we wouldn't really need a control line at all unless we needed the signaling. So during the data transfer phase, after you've set up your call, the control signal is on all the time. So it doesn't have any function during the data transmit phase, data transfer phase, sorry. And the control signal is off or on during the call setup phase. So that's really the function that the control signal is used in. And we will look at some diagrams later on about this. In the other direction, from the DCE to the DTE, we have the receive signal, which is basically the opposite of the transmit signal. So it's a serial bit stream that we receive from the DCE into our DTE. Again, it is used both during call setup and the data transfer phase. And the indication signal I is basically the opposite of the control signal, which we just had on the previous slide. It's used to specify the meaning on the receive data line. It's again on during the data transfer phase, so completely unused basically. And it's only off or on during the call setup phase while the call is negotiated or set up with the digital network. Then we have 2 additional signals which are for clock and timing. One is the S signal, the signal element timing. This provides the bit clock for the receive and transmit data bits. And there's another signal which is optional, is called B byte timing. I didn't really find any references whoever used it. It's specified as an optional signal in the X.21 and related recommendations. And I didn't find any references of somebody using it in or some network using it. At least in the literature I found on the German use of this X.21 interface, the byte timing appears not to be used. So if it is used, it means that both the DTE and the DCE need to actually support it technically. So it needs to be like agreed upon by the specification of the two manufacturers of the equipment. And if it is used, then it indicates the alignment of where 8-bit bytes within the bit stream start. And it's the way it does this is that it's normally high, but it's briefly low during the last bit of each 8-bit byte. In those implementations or those networks where the B signal is not used, there is basically no known alignment of bytes within the bit stream that's communicated on the T and R signals, which is fine since, I mean, for the user data, it's a transparent bit stream. Why would anyone care where the bytes are starting? I mean, if you had such a signal from end to end, then of course you could basically save an HDLC controller at the receiver side or something like that. But yeah, I mean, it's, as I said, it's optional and not used in all the deployments that I've read about. These clock signals, both the mandatory bit timing, the signal element timing, as well as the optional byte timing, are provided by the DCE. And the DCE will normally derive this from some clock from the telecommunications network it is attached to. So the telecom network is the master of the clock, and the DCE recovers that clock somehow from the line. And then the clock is passed on to the DTE to make sure all elements in the network have the same clock and transmit at the same bit rate. So the call setup phase, that's the interesting part. I mean, just having a synchronous bit stream in both ways, the talk would be over by now. It's rather simplistic, but that's sort of where the complexity starts, is the call control, finite state machines, and the call setup phase of the call, with all the things that need to be taken care of. As I said, it's not just calling a peer and hanging up, but it's also, well, it's inbound and outbound calls, and it's inbound and outbound might clash at the same time if sort of you get an incoming call while you're dialing or vice versa. And you have additional signaling status information, as I said, like busy information, subscriber unavailable information, and also some additional, I'm not sure how this would be called in English, but some, let's say, post dialing or whatever, overlap dialing capability in case of private CSPDN exchanges being attached to the public CSPDN network. So that it was envisioned, I'm not sure how well that was deployed ever, but it was envisioned that, like, you have a private branch exchange for a telephony network, you also have the same concept in the circuit switch packet data networks. So inside your company, you have a private CSPDN exchange, which connects to the public CSPDN network. And then, of course, you have some signaling requirements to that regard. Yeah, so the actual signaling information, like the number you're dialing, the subscriber number, and so on, is signaled using a 7-bit ASCII character set, where only some characters are considered valid, all the other ones are invalid. And since it's only 7-bit, one additional bit is used for parity, so an odd parity bit is added to the 7-bit ASCII. So again, we end up with 8-bit bytes. The permitted characters are the SYN character, the bell character, asterisk, plus, comma, minus, dot, slash, and the digits 0 to 9. Every message that's transmitted during this call signaling, call setup phase starts with 2 SYN characters, and it ends with a plus character. So let's say you have the initial dial command of a subscriber. You would send SYN, then the dial string, the number that you dial, and you end with plus. And then this goes to the digital exchange, and the digital exchange will answer with something else, which again starts with 2 SYN characters as start and ends with a plus in the end. The control and indication signals play a key role during the setup phase. And call release is happening rather simple by just dropping the control or indication lines. So as I mentioned before, during the once the call is established during the data transfer phase, the control and indication signals are permanently on. And if either of them drops, it means termination of the call, release of the call towards the peer, who will then respond in turn by also releasing that signal and going back to the off state. So this is the start of a call setup phase in a diagram. I'm sorry that's so small. It's a long diagram in the y-axis, and if I made it even wider, we wouldn't really fit anything on the screen. So what do we see here? We see basically the DTE side on the left-hand side and the DCE side on the right-hand side. State numbers, state names, and also the logical signals of the T, the transmit line, the C, the control line, the R line, the receive line, and the I, the indication line. Note that the control and indication have states called on and off, and the T and R signals have states called 0 and 1, and electrically they are not the same. So 1 is off and 0 is on in that context. So it's a bit confusing. I'm not sure why they came up with different naming for that. Anyway, so we assume everything is idle or ready, how it's called in the state names here, meaning that the transmit and receive signals are at 1 and the C and I signals are at off logical state. And now the DTE wants to make a call, which means it rises both, it changes the C signal to the on state, and it changes the T signal to the on state. Now I'm confused. Yeah, okay. So actually, indeed, then this is basically detected by the network, and the network will then in turn start to send 2 SYN characters, meaning basically that it has, let's say this is the on-hook signal, if you want to think in telephony terms, and this is the dial tone basically from the network side, the proceed to select signal. And then these 2 SYN characters are followed by a long sequence of plus signals. So during the entire dial phase, which is called selection signals here, the network and the DCE are sending plus signs towards the DTE. So these 2 SYN characters and the plus signs are detected by the DTE, which means the DTE can now start to dial, and it in turn sends its dial string, here called selection signal, by 2 SYN characters at the start, and then ASCII characters in this reduced ASCII 7-bit character set that I mentioned before. So it would send the called party number, and then at the end would terminate this message with a plus signal. This again gets sent to the network. Once this has been recognized, the network will stop sending plus signals. Excuse me. Will stop sending plus signals and will again send 1 or multiple additional messages, which each again start with 2 SYN characters. And those could be called progress signals, such as dialing, ringing, and so on and so on. And at some point, that was the wrong key. At some point, what will happen is that the indication line from the DCE is changing state, which means that the connection is established. And at this point, then data can be transferred by both sides. So we see both the I signal and the C signal are in the on state, and here this gray area is the user data that's being transferred in both directions. And here we see an ITU typo, since somebody was writing a French, or was a French native speaker and was speaking about the data transfer. And if now either party wants to clear the call, in this example, it's the DTE that we're looking at, the local side. It just switches the control signal to the off state, which gets detected by the network and communicated to the peer, which at some point means the the indication signal also goes to the off state. And following that, the R and T signals go again to the 0 state, and we end up again in the ready state, which we were at the beginning of this call setup diagram at the previous slide. Yeah, so of course there's similar diagrams for this is an, let's say, an originated call. There's similar diagrams for the terminating call, and they're very complex, surprisingly complex state diagrams for all the timers in different states and what happens when and error conditions that might occur in this signaling process. So let's look at the electrical characteristics. X.21 doesn't specify these. It points to X.27 and X.26 as two different electrical possible interfaces. X.27 then in turn points to V.11. X.27 again doesn't really contain anything but pointing to another spec. And it's balanced differential signals in a similar fashion like you would know from RS422 or RS485. Of course, those two being asynchronous interfaces, but from the signal level and impedances and so on, you can compare those. This variant is permitted for any bitrate up to 10 megabits. And the other option is the X.27, which points to the V10 specification, which is for unbalanced signals and is only permitted for bitrates up to 9600 bps. It's more similar to RS232 in this context, since it's not a balanced signal. I'm focusing on the differential signal, since I assume that in practice it appears to be what most equipment uses, at least based on what I read. I've also found some texts, not in the ITU specs though, that the DCE is always implemented in differential fashion, and only the DTE in a simplistic use case may use unbalanced at low bit rates. And actually, it's intended to be interoperable. So you can use a balanced DCE with an unbalanced DTE. But in practice, this probably has caused quite a number of problems. As you can find from some articles about issues with signal integrity and having to put series terminations, resistors into the lines if you have interoperability problems between those two versions and so on. So it looks a bit like a nightmare. I'm not sure why they specified two different ways. It's probably country A said, well, we want this, and country B said, we want the other. Maybe Germany and Japan, I don't know. I think European countries and Japan were quite involved in those specs. So if we look at the timing of the and the electrical signals, we have for binary signals, and both signals have an A and a B line in both implementations. So even the non-differential has an A and a B line in the connector. And if the difference voltage is less than minus 0.3 volts, then it's a logical 0 for a data line or an on in a control line. And if it's the other way around, if it's larger than plus 0.3 volt, then it's a logical 1 for data or an off in a control interface. And if you look at this diagram, which is not in the spec, of course, it would be way too simple if the ITU would specify such a diagram. You could understand what happens. Of course, the ITU specs only contain a textual description of this, but this diagram was found in a German book on this subject. So you can see here we have the S, the bit clock rate. Ein is on and ours is off. So we have a bit clock, a nice 50% duty cycle square signal. Then we have here the optional byte timing signal, which goes low for half a bit duration in the last bit, the 8th bit of every octet, if it is implemented. Here we have the T line, the transmit from the first bit to the last bit, and again the first bit next. And here we have the control and other lines, and these arrows here indicate that basically during in this logical view of off and on, in the rising slope, you get you change the signal. Basically the transmitter changes the polarity if needed, and the receiver then samples at the center of each bit, which is indicated here in this example here. So the signal changes at the rising slope, and the signal is sampled at the falling slope of the clock. Interestingly, this has changed between the 1988 and an earlier version of the spec. God knows why you would change such an important part of the interface. Yeah, but well, no comment. So yeah, that's the logic levels and the timing. And in terms of connector, yeah, I forgot to add a picture, but I think on the next one of the next slides we will see one anyway. So it's a 15-pin sub-D connector. Those who have used PCs a long time ago will know it as a game port connector. And it's specified not in X.21, but X.21 refers to ISO 4903, which I couldn't find any copy of online, and I'm not going to pay more than 100 euros for a spec that's, I don't know, 40 years old or whatever. But I found some other literature which states that ISO 4903 claims that the DCE shall use female and the DTE shall use a male connector. And the interface point, the reference interface point, is the physical connector at the DCE, so that the cable is already part of the DTE and thereby in the responsibility of the user. And anything up to the female connector in the DCE is the responsibility of the telecom operator. So yeah, what kind of interfaces can you find today to speak X.21? Christoph raises the question whether how does this compare to V35 with these old bulky US Amphenol connectors. I didn't analyze it myself. I just found a contemporary article which said, well, it is something for study in the international community. So not sure whether that study ever ended at some point. I think V35 is relatively similar, but probably without this all this signaling. I never looked at it in detail, to be honest. The Cisco interfaces that I'm going to mention here right now, they offer V35 and X.21 from the same interface. So I think, not sure what they're switching internally, or if they switch anything, or if it's just the adapter cable that you use. But it seems to be possible to build interfaces that can do both. Let's state it like that. So yeah, what can you find in terms of equipment today, inexpensive for some pet project? Well, you find all these line cards for all the Cisco equipment, and the one-port ones like the WIC1T you can get for 6-7 euros on eBay. The larger port number ones with 4, even 8 interfaces, of course, they're more expensive since they're more enterprise. And also the associated routers, of course, like the 2600 series, for example, you can get also for a few bucks. So that's very easy. Also, you can find null modem cables for X.21 for Cisco, so you can connect 2 Cisco devices back to back. That's apparently a setup that many people use for some Cisco exam, or have used for Cisco exams, which apparently until not so long ago is still covered setting up synchronous frame relay interfaces. And in order to play with something like that or prepare yourself for the related Cisco exams, people would buy 2 routers with those X.21 interfaces and then connect them over crossover cable. And then it's used for HDLC-based network traffic, so Cisco HDLC or whatever variant, frame relay or whatnot. but it doesn't really have support. At least I'm not aware that any Cisco equipment ever had support for these the signaling and this call setup phase and all that that is required in the CSPDNs. So basically, that equipment I think was introduced at a time where the CSPDNs were already dead, and X.21 was only used for leased lines anymore, or for leased virtual lines, leased data services, point-to-point data services from operators. And all of this signaling stuff was no longer needed. You can also find, and I actually found one for an affordable price, these Farsight is the company, FarSync is the product name, cards. What you see on the right-hand side here is a T2U card. It has two 15-pin DSUB connectors for X.21. And this is a PCI card still, which you can find, and even the PCI cards are sold relatively expensive on eBay. If you have a lot of money, you can still today buy PCIe cards doing the same, but much to my disappointment, they also, again, only support HDLC-based network traffic, and no support seems to be included for this circuit switched X.21 as it's used in CSPDN. So it's not really useful for this. And as a result, basically the conclusion was we need some kind of do-it-yourself X.21 hardware to really cover all the use cases in order to talk to all the legacy equipment, for example, Teletext user devices. So what kind of requirements do we have for such a do-it-yourself X.21 USB adapter? Well, it should support the full X.21 signaling with the call setup, call tear down, and all of that. It should ideally support DTE and DCE role, meaning that you should be able to emulate a network towards an end device, and you should emulate an end device towards a network. Should also be able to passively sniff in order to help with debugging and so on. And here, Christian Vogel and myself, we've been doing some early design and planning work for the electrical interface. So we had two different ideas and discussed, and finally we go ahead with what Christian Vogel has proposed. Yeah, so the plan is to do a board which only contains all the isolated transceivers for this differential interface in a way that you can implement both of roles and all the functionality stated above, and then just have a pin header where you can connect to a microcontroller or FPGA board. So we don't constrain ourselves what we do in the end. Microcontroller software-based approach, for example, with an RP2040, is certainly a more accessible approach to people mainly doing software development. But if everything else fails, we might need to turn to an FPGA. But I think the requirements are, especially at the interface speeds that we're talking about, up to 64K in those networks, we should certainly be able to do that all in software from a microcontroller, in the worst case with bit banging, but the PO units of the RP2040 should help us there. There is a Osmocom ticket for this, so if you're interested in that, you can watch or subscribe that and see the updates and the discussion that's happening. There's also a Git repo already, but it only contains my outdated proposal based on Sylvain's RS422 design. So yeah, it's still early work at this point, but at least we have a plan of what we want to do it, and I hope to have some progress at some point. And that brings us to the end of the introduction, what I wanted to show. And with that, are there any questions or comments or feedback on the record? Still part of the recording at this point? Let me know.
So, hi Harald, thanks for giving the overview. Could you do me a favor and go back to this trace with the signals over time, because maybe you said it and I have just not the one with the call setup, you know, the different states. Yeah, here, because did you mention it, or so is the kind of this, I would call it a break condition, so a elongated zero on the T. Is this kind of the trigger for the whole thing? Because I think it's normally staying in the state for quite some time, right? Because it was the same like ending the actual connection.
So the initial state of the lines that you see here, that can stay indefinitely. So that's the idle state, or they call it the ready state of the interface. And the trigger basically starting all of this is these two slopes that you see here.
Okay, yeah, I probably, after the second slide, I didn't remember it correctly anymore. Yeah, thanks.
So if we go to the next slide, then you see basically they go back to that state where basically all the signals here are on the right hand side of their column, meaning here on the one state for the T and R, and on the off state for the I and C signal. So we're back to origin, and yeah, that's the ready state. And if there's also there's lots of stuff that I didn't mention. I say it's just simplified, but there's also a way how for example, the DTE could say, well, I'm not ready to accept a call, in a way that the DCE in the network already knows. Don't ask me what this is. Maybe it's just the C line up, or I don't know what exactly. There's also some special bit patterns that you can have in the data, like an alternating 01010101, which has a special meaning in the transmit or receive circuit. And there's also an alternating nibble with 4 zeros and 4 ones, which has another meaning. So there's all kinds of interesting details that I didn't really present here, which are also not super critical, I think, at this point.
But doesn't that explain why one is off? If you are on an unbalanced circuit, the only state you can detect is one. And if you get a breakage of the cable or the line, you get zeros. So that a breakage needs to become on, because that means that it busies out all the equipment automatically.
Possibly, yes, but then we say an unbalanced. If you look at the electrical bits, as I said, I didn't really look a lot at the unbalanced side, but the specs that I found, or the literature that I said, this is still true even for the unbalanced link. So it's basically a negative or a positive voltage, and you still have like if in an unconnected state, you would have basically probably something. Like if you have a line that's not connected, then you wouldn't have less than minus 0.3 or more than plus 0.3 volts. You would have something in between, right?
Yes, that's true. I'm just thinking because telex, the type teletypewriters, do have similar weirdnesses where one is current flowing, and current means line is not broken, I'm ready to receive.
Yeah, I mean, to me, I mean, if I find some explanation, it's fine. But if not, it's also fine. I mean, in the end, we just have to implement it like it's in the spec, and
it's a negation.
Yeah, I mean, whether it's left or right, I mean, okay.
Yeah, still, I think A and B is the other way around than RS 485 from the polarity. But I think one has to just try it out to be sure with all the different definitions.
Yeah, I mean, since we in the preparation of this talk, which happened after Christian and I spoke last, I found some rather good German literature that covers the spec, so I'm quite sure that helps a lot with the implementation now. It's basically in these Taschenbuch der Fernmeldetechnik from 1989 covers the electrical side, and from 1990 there's an article that covers the call setup side. And particularly it also covers sort of interesting things that were present in the German network which are not part of the spec, like artifacts of how the switches behaved and so it seems rather interesting to look at those. Yeah, and the other thing which I haven't shared yet wider here is that I just received a loaner of a teletext test device from Wandel and Goltermann. It's a nice suitcase. The equipment looks like it's new and unused. I mean, even the buttons and everything looks like nobody has ever pushed them. It's not a single scratch or use mark or something like that. This device can behave as a DT, as a DCE, as a tracer. It can print traces on a thermo printer that's included, and it can even simulate the entire circuit switch packet data network between two teletext devices. With that device, I think we should certainly be able to see exactly what we need to do and how in order to do the same in open source software.
Do you know how the synchronization of the timing was done on the national level? I mean, if you connected to the network in Munich and you connected in Hamburg, you were supposed to have the same timing, but they probably didn't have the same timing source. So
I'm not so sure. So to be honest, I don't know. I mean, it's related to this EDS exchange that was used in the German network, and well, actually, now that I remember it, it might not even have been necessary to do so, because the EDS exchanges actually they didn't do synchronous sampling of the subscriber signals, but they transported. It's a very odd thing. I briefly mentioned it in the previous talk. So the line interface circuitry of the exchange that was basically on the other side of the DCE line, it detected polarity changes on the subscriber side of the line, and then communicated those polarity changes to the remote side. And so actually that was not done synchronously in a way. So it's normally you would assume it's a synchronous network. So basically, yes, during every bit clock, the input signal is sampled once, and then you basically take that state and you push it to the other side. But actually, it was not based on sampling in the center of each bit, but it was based on some autonomous devices that detected polarity changes, and then those polarity changes would be signaled. I'm not sure if even synchronously to the other end.
So it's like if you're pushing Manchester coding through the nation, right?
Yeah, something like that. So I didn't really look at it, at least inside the exchange. Definitely it was this kind of slope detection and not synchronous bit sampling, but how they did it between the exchanges, I'm not sure. But I can point you to a book which I've also scanned that should give all those details, I guess. Yeah, it's seriously strange that they did this strange slope detection, but I even found a rationale of why, but I forgot it again. I didn't really understand the rationale. I mean, they gave one, but it didn't seem logical to me. But yeah, well, who knows why, how?